So can you see my screen?
Bado, not yet.
Not yet.
Let me put on the... You can't see the screen yet? Eh?
Yes.
You can see or you can't see?
We can't see.
We can't see.
Okay, let me try to share it a second time. And now, can you see anything?
Yeah.
Yeah.
Yes, we can see.
The first word should be example.
Yes, it is.
Good. So we can now proceed. So this question asks the following. We prove the law of cosines for plane triangles. You may have proved this using different techniques, but now we are going to show you how you can do it using these cross product and so on, and dot products. Actually, we'll use a cross product in particular and mix it up. So we'll set up a triangle as follows. We have a triangle with the sides A, B, and C. So we set it up in such a way that the resultant of the three vectors is 0. That is one way to set up a triangle. You can also set it up so that one of the vectors is a resultant of the other two. That will still work. But here we have A plus B plus C is equal to 0. So you can see that because if you move from A, you go to B and back to C, you end up exactly where you started. So you have not moved. So in terms of vectors, that is just a 0 vector. So if A plus B plus C is equal to 0, you can get a cross product of both sides with A, and that will be equal to 0 because the cross product of A and 0 will be 0. On the other end, we'll be left with A cross B and A cross C. Now, A cross A will disappear because A cross A is equal to what? Why is A cross A missing in this next
0. A
Yes,
cross
because-
A is equals to 0.
Correct. So all you're left with is this, and you can now rewrite this as A cross B is the same as minus A cross C. But based on the properties of the cross product, this again is the same as C cross A. So with the same ideas, we can now cross both sides of this equation, but with B. When we do that, we end up with this conclusion that B cross A is the same as minus B cross C. But we know from the properties of a cross product, minus B cross C is the same as C cross B. We do the same for C. We get the cross product of C with both sides of this equation. So we have C cross A. What survive? The only two that survive is C cross A and C cross B. C cross C again will be 0, so it doesn't appear in the next line. And when you simplify, you have C cross A will be equal to minus C cross B. Again, using the properties of a cross product, we know that minus C cross B will be equal to B cross C. So looking at all this, we can see that A cross B, where is the first one? A cross B is equal to C cross A. And we also know that B cross C is also equal to C cross A. So it means all these three are equal. Now, using that and the definition of a cross product. Oh, I didn't complete this. Or did I mix up the pages when? Yes, I think now there's a mix up with the pages. This should have been page 1. So we'll skip this page. The problem continues on the next page. So it means that if you get the magnitudes of these 3 vectors, they should be equal. And the magnitudes of the 3 vectors are simply given by the magnitude of A multiplied by the magnitude of B times the sine of the angle between them. Remember the way the triangle is set up, the angle between A and B is capital C. Usually the angle is indicated using a capital. I think you did this in high school. The standard way of just naming a triangle. You're familiar with that, right?
Yes.
Yes.
Yeah. So then this is the magnitude of B. This should be a vector. Magnitude of C times the sine of A, and the magnitude of C times the magnitude of A times the sine of B. So if we divide throughout by this product, A, B, and C, it simplifies to the sine rule or the sine law that you are familiar with. So we can derive the sine law also using the cross product. Earlier on, I think we proved also the cosine law using the dot product. Or the cosine rule, if you want to call it that. The next example, this is now what should have been page 1. It says that prove that the area of a parallelogram with the sides A and B is A cross B. So now you already know how to find the area of a parallelogram. It's usually the base multiplied by the height, right? Now A and B don't have to be equal. The way I have drawn them makes them appear to be equal, but they do not have to be equal. If they're equal, then you have a rhombus, which is still a special case of the parallelogram, and the formula will still work anyway. So we know that the area should be the base or the length of the base multiplied by. So the base would just be the magnitude of this vector. And if you draw a perpendicular from the terminal point of this vector A and drop it to the vector B, you have a right angle triangle here. So the height here is simply using the trigonometric ratios. You should be able to see that the sine rule, the height will be the length of the hypotenuse multiplied by the sine of this angle theta between A and B, right? So it means the area, this is supposed to be area, not A. So this should be area. The area should be equal to the magnitude of A times the sine of theta, which gives you the height, multiplied by the length of the base. And that simplifies to magnitude of A, magnitude of B, multiplied by the sine of theta. But from the definition of a cross product, we know that this is precisely the magnitude of the cross product. So the magnitude of the cross product simply represents the area of a parallelogram with sides AB. So using the same ideas, you can find show that if you have a triangle with sides A and B, 2 of the sides are A and B, then you can always find the area as half multiplied by A cross B, because this is just half of a parallelogram. So you get half of the area of the parallelogram will be the area of this triangle. So this one you can prove in your own time. So we move to the next topic, which says triple product. So we have had one. What's going on? So we talk about triple product. We we've had two types of products. We have, at some point, we have defined the scalar product or the dot product, which involves only two vectors. And then we have also defined the cross product for two vectors, though it can involve more than two vectors. So we want to consider the cases where the products involve more than two vectors. When working with the dot product, because the dot product of two vectors is a number, you cannot, getting the dot product of three vectors will not make sense. But it makes sense to get the dot product of a vector and the cross product of two other vectors, because this is a vector and that's a vector, so you can get the dot product. So these products where you have A dot B cross C, where B and C are vectors and A is a vector as well, is called the scalar triple product. Triple because you are working with three different vectors. So that's one type of triple product. The other triple product you can define is the cross product of three vectors. So you have A cross B cross C. But here you have to be careful because the cross product is not commutative. So these brackets, where you put these brackets, and how you order the precisely how you order the vectors makes a big difference. For instance, if you have this as C cross B, that would be a different product, because B cross C is the same as the negative of C cross B. So how you order these is really important, the cross product. So in this case, this triple product of three vectors gives you another vector. The scalar product will be the dot product of two vectors eventually, so you'll end up with a scalar, right? And that's why it's called the scalar triple product. And this one, the cross product of vectors, always gives you another vector, and that's why it's called the vector triple product. So let's see how we can interpret this triple product. So this one says that A dot B cross C, show that A dot B cross C is in absolute value equal to the volume of a parallel pipe with sides A, B, and C. So a parallel pipe is basically the three-dimensional equivalent of a parallelogram. So you basically like have a cube with the sides slanting. A cube itself will also be a parallel pipe, but in general, these sides are not necessarily perpendicular to the base. So what we have is that the base and the top are parallel, and then these two sides are also parallel. That makes a parallel pipe. So the claim is that this dot product, A dot B cross C, will be the volume of this parallel pipe. So how do you find the volume? Volume is simply given by the height multiplied by the area of the base. Now, if you want to find the height of this, the height is basically the projection of this vector A on the normal vector. If you project A on this unit normal, N is a unit normal which is perpendicular to the base. If you project A on N, you will get the height, right? That will give you the height. I didn't draw the, it's here. The height is this. It's the same as projecting this vector A on the unit normal, which is perpendicular to the base. So this gives you the height. And then you have to multiply that by the area of the base. Now the base is just a parallelogram with sides B and C. And the area of that parallelogram is simply the magnitude of the vector B cross C. So these are two numbers. The magnitude is a number multiplied by the dot product, which is a number. So these are two numbers which give you the volume. So this now can be written as A dot B cross C multiplied by a unit vector N. But you see, N is perpendicular to B cross C, which is fine. So it means this is the same as, this whole thing is just the same as A dot B cross C. So you need to see that B cross C n is the vector in the direction perpendicular to B cross C, whose magnitude is this, B cross C, right? And this is precisely the definition of the dot product of A and the vector B cross C. I hope that makes sense. You will take time and read this carefully. So here is another result. It says for any three right-handed sets of vectors, A, B, and C, that are not in the same plane, so they're not coplanar. You learned about planes in geometry, right? You learned about planes in 2 dimensions.
Bado hatujafanya.
You have not done SMA 105?
Oh yes, we've
Tumefanya
done.
hao.
Hey, munakumbuka Manchester United lakini geometry hakuna.
Tunakumbuka.
Hatulifanya.
I will add some football questions, don't worry, to make it fair.
UEFA.
Yeah, so A dot B cross C, it can be shown that if the 3 vectors are not in the same plane, then A dot B cross C is equal to B dot C cross A, which is equal to C dot A cross B. Now, let's just go back a step. So you can imagine if these 3 vectors, if A, B, and C are in the same plane, then the volume will be 0, right?
Yeah.
Yeah, if A is actually on this plane, the same plane as B and C, then the parallelepiped has no volume at all. It will be flat. And that means that this dot product will be 0. So this tells you that if you have 3 vectors which are in the same plane, then A dot B cross C will be equal to the 0 vector. 0 the number, sorry. The volume will be 0 basically. So this A dot B cross C will be equal to 0 if they're all on the same plane. So let's see if we can prove this result. The result that these 3 A dot B cross C is the same as B dot C cross A, which is the same as C dot A cross B. So what you really need to see is that these 3 all represent the volume of the same parallelepiped. So if you go back to the diagram, although here I'm using the capital A and B, still the same idea, you can get the volume of this parallelepiped by taking the base to be this plane of A and C. So if you take the base to be the plane of A and C, this will be B dot A cross C, right? You can also take the base to be the plane of A and B. And if you take the base to be the plane of A and B, now the volume will be C dot A cross B. So they all represent the same thing and therefore must be equal. So that's one way to prove it. You can also prove it directly if you wish. That can be done. I've just used the fact that is the volume. Make a difference. So if you notice, before I proceed, the proposition said that rather this example said that the absolute value is equal to this. The reason we can do that, we have to think of absolute value is because of the following. Here we have assumed that these 3 vectors, A, B, and C, they form a right-handed system. So A, B, and C form a right-handed system. That means if you point your right-hand fingers from B towards C, then the thumb will point in the direction of A. So these 3 form a right-handed system. But if they form a left-handed system, then this normal will be in the opposite direction. So what will change is that what will happen is that this thing will change the sign. It will be negative now. And the area usually is not a negative number, so that's why you have to get the absolute value. The only thing that will change it is the sign. So for you to get the area, you get the absolute value of this quantity. That's why the question says that in absolute value, this part here says absolute value. That's why it says that. So there's another way of considering this. That is when the three vectors form a left-handed system. And when they do, this will change sign. It will be negative.
Kuna watu wako nje kwa lobby.
There are people
waiting to be admitted.
I've admitted them. But I think it's 30 minutes later. It's important for you to try to join the class on time. Unless you have something that's more important you're doing. Anything you do in life, you really need to go through your choices. Unless you're doing something that's more important than the class, maybe you should be in class. So you really have to make a correct decision every time. You have to choose, make the right choice. And if you think what you're doing is more important, you have to be able to convince yourself that it's more important than class. If you can't convince yourself, maybe you should just come to class. It will save you a lot of time. But of course, the technology challenges sometimes. That happens. But when you can come to class on time, please do. So here is how to compute this triple product if you have the vectors written in this form. If the vector A is written as A1i plus A2j plus A3k and so on, up to C written as C1i, C2j, C3k, then we can show that the dot product A dot B cross C is simply the determinant of this matrix, where the first row are just the components of I, J, and K in A, the vector A, and the same for the second. B1, B2, and B3 are the components of B, and C1, C2, and C3 are the components of C. So one way to do it is just to do the direct computation. Not competition, computation. We know how to compute B cross C. The B cross C is the determinant of this matrix. We know what A is. We can leave it intact there. So A dot B cross C would be A dot multiplied by the determinant of this matrix. That will be also a vector. So A is this thing. And when you get the determinant of this matrix, you get what is in the square brackets. It goes on up to here. So now you can expand this further. You get the product of A1i and the whole of this thing, and so on. So what will happen is that if you get some of them will vanish, some of them will be retained. For instance, if I get the dot product of A1i and this first term, I know I dot I will give me what? What is I dot I?
That I is 0.
I dot I is 1. You guys should read this mathematics. I will tell Super Sports to stop airing live games.
Dot is 1.
Eh? Until you start doing mathematics. Now, the next product will be A1i. This is A1i. And with this B1, B3C1 minus B1C3 J. So you'll have I dot J here. And I dot J must be?
I think
0.
there's a mistake.
0.
So this term will vanish. Then the other one that you will do is A1i. Get the dot product of that with this, right? So you'll end up with I dot K somewhere, and then multiplied by these two numbers. This number B1C2 minus B2C1 and A1. But what is important here is I dot K will be equal to 0. So this will also vanish. So with the first multiplication using A1i, the only bits that survives is this. A1 multiplied by B2C3 minus B3C2. That is what I have here as a first term. Then you move on to multiply, get the dot product of A2J and the whole of this. Now the only survivor in that product will be A2J and this second term, right? Because J dot J is equal to 1, and J dot I will be 0, and J dot K will also be 0. So the only survivor will be A2 multiplied by B3C1 minus B1C3. And that is this second term, right? Then you do the last one, and already now you can guess which one will survive. Which one will survive? So in between this step and this next step, there's some work to be done. So I'm explaining to you what to do. Better find time to do it yourself. So A3K will be multiplied by this coefficient of K, because K dot K will give us 1, but K dot I is 0, and K dot J is also 0. So the only survivor will be A3 multiplied by B1C2 minus B2C1. So when you simplify, this is what you end up with. Now what you have here is precisely the determinant of this matrix. You can compare, try to compute the determinant of this matrix. You will see that it's exactly what you have here. So what we have shown is that A dot B cross C is just the determinant of this matrix, where the first row are the components of A, the second row the components of B, and the third row would be the scalar components of C. So let's see an example. We need to evaluate this vector. So take this as your A, 2I minus 3J, get the dot product of that with the cross product of this vector, I plus J minus K, and this other vector, 3I minus K. So based on our formula, the answer to this should simply be the determinant of this matrix, whose first row are the components of this vector here. So this vector, the components are 2, 3, and there's no K, so the component for K is 0. So we have 2 minus 3 and 0. Second vector is 1, 1 minus 1. That's what appears in the second row. The third vector here does not have J, so the J component is just 0. So we'll have 3, 0, and negative 1. Remember, we must order them. The component of I first, followed by that of J, followed by that of K. So here you must put the 0 component for J, because J is 0. And you'll have a third row, 3, 0, negative 1. Now the determinant of this is equal to 4. Your work now, I'll give you some work now. Can you confirm that this determinant is equal to 4? You'll have 2 minutes. For this one, there's no reward. You'll just do it for the love and honor of mathematics. Hii ni ya kujitolea.
Yeah, done.
So you agree with the answer? It is 4.
Yes.
So another way to solve this is to expand it directly. Remember when we were proving this, we just multiplied these things out. So you can also just do the same thing, multiply them out, and you end up with your answers. Or you can use a shortcut where you just work with the determinant of this matrix. So if you can't remember the formula, you still have the option of doing it the hard way. Just multiply out and make use of these properties that I cross I, J cross J, and K cross K are all equal to the zero vector. Should be an equal sign here. And then I cross J and J cross K and K cross I, you know their values. What is I cross J?
Cross
Pardon?
K. I cross J, K.
Correct. And J cross A is what? J cross K is what?
I.
And
Ah,
K
no,
cross,
negative. Oh,
just use your right hand. If you point your fingers in the direction of J from K, from in the direction of K, where will your thumb point? It will point in the direction of I, right?
I. Yeah.
So your hand is your calculator. Use your hand, your right hand. And K cross I will be
Negative J.
Are you sure?
No. It will be positive. Positive J.
Yeah, that's correct. So once you know those values, any point where you encounter I cross J, you replace it with K and so on. And so on. Anywhere you encounter J cross K, you replace it with I. And K cross I, you replace it with if they are reversed in order, you replace it with a negative, right? So you have to watch the sign, because if you have I cross J, that will be I. If you have J cross I, I cross J will be K, but J cross I will be negative K. So you have to be careful when working with the cross product. So you keep track of the sign. So here is an example. Can you prove that A dot A cross C is equal to 0? So here is your, try to do this one. Once you do it, you can explain to me what you have done. I'll give you 2 minutes. So you could think of A in terms of the I, J, and K, and so on. So you'll have A appearing twice and C only once. So you can write this as vectors. So this should be vectors. I keep forgetting to put the bar. So that should be bar A, and bar C. Nani amemaliza? You actually don't need to calculate this. There's a simple answer to it if you understand the properties of the determinant of a matrix. You said you covered matrices last semester. So I think I will also cover the topic of matrices a bit later on, so that we can recover what we have done. But inaonekana hiyo mmeshindwa. So let's go back to this. If you want to solve that one, what happens is this. If you're getting A dot A cross C, then this first row and this second row will both have the same numbers, right? Unanisikia?
Yes.
Yes, they will have the same numbers. So what happens for a matrix? Any matrix which has two equal rows will have determinant equal to 0. So that would be your argument. If a matrix has two rows that are equal, then the determinant will be 0. So if this second row is also A1, A2, and A3, this determinant has no choice but to be 0. And that means, which is precisely what you get when you compute this A dot A cross C, you'll get a matrix whose determinant is 0. And therefore, this must be 0. It's 0 because it has two equal rows. So and that's the same for columns as well. Even if the matrix has two equal columns also, the determinant is 0. So also, it can be shown that for any three vectors, A and B, A, B, and C, then A cross B cross C can be written as a linear combination of B and A. So basically what this says is that A cross B cross C, this vector should be in the plane of B and A. So you have to be, so let's see if we can figure this out. So A cross B cross C is a cross product of two vectors in the following sense. The first vector is A cross B, and the second vector is C. And when we get a cross product of two vectors, the result should be perpendicular to both vectors. So this whole result must be perpendicular to A cross B and to C as well. So this means that A cross B therefore must be perpendicular to the plane of A, and we know that A cross B rather is perpendicular to the plane of A and B, right? So this forces that A cross B cross C to be perpendicular to C as well. And it must be in the same plane as A and B. I think I have a diagram that explains that. So that means it's since the A cross B cross C is in the plane of A and B, it means it's possible to write it as a linear combination of A and B. So it's possible to find these scalars. Now, I will not go into the details of how we obtain these scalars, but now alpha will be A dot C, and beta will be minus B dot C. So alpha is A dot C, and this second scalar beta will be minus B dot C. I don't know if I didn't draw the diagram. You can try to draw this. You have three vectors, A, B, and C. If you get A cross B, it should be perpendicular to the plane of A and B. And A cross B cross C should be perpendicular to the plane, to both the two vectors, A cross B and C. When you draw it out, you will be able to see now that the cross product of the three, now it should be in the plane of A and B. Try to draw this. But what is important now is to get this formula. I need you to capture this formula. When you want to compute A cross B cross C, this is how you will compute it using this formula. You could also now use I think this is fine. So there's something else that we call the direction cosines. So what are direction cosines? So first of all, we'll set up the following background. We determine the angles alpha, beta, and gamma, which the vector r here makes with the positive directions of the coordinate axis. So alpha will be the angle it makes with the x-axis, positive x-axis. Beta will be the angle which the vector makes with the positive y-axis. and gamma will be the angle which the vector makes with the positive x-axis. So it also claims that cosine squared alpha plus cosine squared beta plus cosine squared gamma will be equal to 1. We shall show all that. So let's check the diagram. If our vector is this red arrow here is the vector r, and the terminal point is x, y, z, so that the position vector here is xi plus yj plus zk. You write it in that form. Now this vector is in the air, but you can measure the angle it makes with the positive x-axis, and that is what we call alpha. So you can see this angle here that the vector makes with the positive x-axis, that's alpha. The same vector also will make an angle with the positive y-axis. This is the y-axis. So that angle is called beta. And the positive, and also it will make an angle gamma with the positive z-axis. So make the following observation. This, we draw a cuboid. So these are straight lines. This is like a box. And when you do that, you observe that this triangle, OAP, must be a right angle triangle, and the right angle is at A, right? Can you all see that? Are you with me? This OAP is a right angle triangle. You agree with me on that one?
Yes.
And the right angle is at A. So if you apply the trigonometry that you know, you should be able to see that the cosine of alpha should be equal to x. X is this distance, right? That's the distance x, divided by the magnitude of the hypotenuse, the length of the hypotenuse, which is just the magnitude of r. Using the same argument, you should be able to see that the cosine of beta is also this distance from here to here. That distance is y. And you can draw a triangle. I didn't name this point, but if you can call it Q, if you call this point Q, then OPQ will be right angle triangle, and the right angle will be here at Q, so that the cosine of beta will be equal to this distance, the adjacent over the hypotenuse, right? So the adjacent will be this y, and the hypotenuse will be again OP, and the length for OP is just the magnitude of the vector r. The same idea also will help you get the cosine of alpha, which is z over the magnitude of r. Now you will notice that now these are the these are called the direction cosines. Now if you add up the squares of these cosines, you have cos squared alpha plus cos squared beta plus cos squared gamma. It will be the same as adding up, get x squared over magnitude of r squared plus y squared over the magnitude of r squared again plus z squared over the magnitude of r squared. And you will see that that simplifies to this. But what is up here, x squared plus y squared plus z squared, is the same as the magnitude of r squared. So you can replace it with that, and so that the numerator and denominator are just the same thing, and therefore that must be equal to 1. So we have proved that the sum of the squares of the direction cosines will always be equal to 1. So we can also make the following definition. The numbers cos alpha, cos beta, and cos gamma are called the direction cosines of the vector OP. So a unit vector in the direction of r is simply given by the vector r divided by its magnitude. So that turns out to be the same as what you have on the right-hand side. You divide every component by the magnitude of R. But you notice again, we saw earlier that this is the same as the cosine of alpha. This is the cosine of beta. It's a cosine of gamma. So we can write a unit vector in the direction of R as this. So, and you can check that it's a unit vector because the magnitude will be equal to 1. We know that cos alpha, cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. So that is done. We have proved, we have shown something extra. We did more than what was asked. Initially, we were supposed to just show that this is equal to 1. This sum of the squares of a direction cosines is equal to 1. But we have gone further to state that a unit vector in the direction of R can be written in this form, where the component of I is cos alpha, component of J is cosine of beta, and the component of K is the cosine of gamma. So the plane, I think that's, now we move to a new topic. Are there any questions on what we have done? Any questions? Mmeelewa kila kitu? You want to read faster? You are being very careful. Hamtaki kujaibisha?
Yes.
Hamtaki aibu ndogo ndogo. Okay, let's continue. We discuss, now we'll talk about the plane, and we'll discuss the various forms of describing the plane. So if we have n is a unit vector, this doesn't make sense. So I'll explain this. This is a part of a plane. So it cuts the x-axis at the point A, the y-axis at the point B, and the z-axis at the point C. So the vector itself is R. It goes all the way to P. Sorry, N. There's a perpendicular vector from the origin up to P. That measures the distance from the origin, the plane P, the shortest distance rather, from the origin to the plane P. And that shortest distance is what we call the distance from the origin to the plane. Right? So then N is a unit vector in this direction. So N is not, as described here, N is not a unit vector from the origin to the plane. It's just the unit vector, unit normal vector, or the unit vector in the same direction as the vector that is perpendicular to the plane from the origin. I don't know if that makes sense. So what I'm trying to say is that N, this unit vector, in the same direction as the vector that is perpendicular to the plane, may not even get to the plane itself. It will be just, unless that distance is 1, it will not reach the plane. If the distance is smaller than 1, it will exceed the plane. If the distance is less than 1, the vector will be under the plane, right? Is that making sense? You need to respond. So it's important to understand the diagram before we proceed. So this point P, this n actually should be just part of this vector. This vector, the distance here is P. So the whole of this cannot be n because n is just a unit vector, its length is 1. So n will just be a vector maybe from here to some point there. And then this vector will be this length P multiplied by this unit vector. That will be the vector from this point to that point, from the origin to the plane here. So I've just pulled out this triangle. So this vector is normal to the plane. That's why we have a right angle here. Good. I hope you have understood the diagram because it's important to understand the diagram before we proceed. So if you pick any other point P on the plane, this distance from the origin to the plane will simply be the projection of P on the normal. Right? If you project this vector R on this normal, the normal is here, but the projection can be longer than the vector itself. So the length, if you project R on N, it will stop here because you have to drop a perpendicular to this vector. And then the projection is just the length now from here to the point at which the perpendicular hits this vector. So if the vector is shorter, you have to extend it. In this case, N will be shorter. So you have to extend it in that direction to get the projection. Right? So this distance from here to here, we know is P. And the projection of P on N is just, of this vector R on N is just R dot N. So we can get, for any point on the plane, this equation will always be true and will therefore define the equation of a plane. So now we also know that if the direction cosines of this vector, this normal vector to the plane, it will make some angles with the x-axis, the angle alpha with the x-axis, beta with the y-axis, and gamma with the z-axis. So this will be the direction cosines. Cosine alpha, cosine beta, and cosine alpha will be the direction cosines of this vector. So a unit vector in the same direction we saw earlier can be written as, so the unit vector n will be just cos alpha I, cos beta j, and cos gamma k. And r can be written as xi plus y j plus zk. So you get product of r and n. This is what you end up with. But we know that r dot n is equal to p. So you get the cross product, the dot product of these two vectors, and they will be equal to p. This gives you the equation of a plane. This works if you know the angles. If you don't know the angles, then you can't use this form. But this is what we call the normal form. So another way to write this is to replace, you know what cos alpha is? What is cos alpha?
X over R.
Pardon? Yeah, we shall see how to do that in a short while. So let's apply this to an example. Find the equation of a plane which is at a distance 5 from the origin and perpendicular to the line joining the 2 points 1, 0, 2, and 2, 2, 4. So the plane is perpendicular to the line that joins these two. So if you want to find a vector that is perpendicular to the plane, you find a vector that is normal to the plane, you will get the vector that runs from 102 up to 224. So the position vector of that vectors joining these 2 points will be the difference in the coordinates. You get 2 minus 1 as your first coordinate of the normal, 2 minus 0 as your second coordinate of the normal, and 4 minus 2 as your third coordinate of a normal. So this gives you the position vector of the vector that is normal to the plane. But you don't want the position vector, you want a unit vector in the direction of this normal. And that means you have to divide it by its magnitude. So the magnitude, this is something is not right. Yeah. But it's fine. This is 2, 2. Sorry, this is 1. This is 2, and that is 2. So the magnitude of this vector will be 1 square root of 1 plus 2 squared plus 2 squared. You can see that, which is 1 over 9. 1 over square root of 9, which is the same as 1 over 3. And on this end, we have 1, 2, 2. So this gives you the unit normal. Once you obtain the unit normal, then you can find the equation of a plane. Because any point on the plane dotted with this should be equal to the distance from the origin to the plane. So the distance from the origin to the plane is given as 5. So pick any point on the plane, get the dot product of that point with the unit normal. You will get the distance from the origin to the plane, which is written on as 5. So that's what we do next. So take this as a position vector of any point on the plane, and r dot n will be equal to 5. So that this vector dotted with this vector should be equal to 5. And the dot product, now multiply both sides by 3 to get 15 on this end. Then you get rid of a third on that side. And just get the dot product of these two vectors. X dot 1 is the same as x, x, y, z dot 1, 2, 2 is the same as x plus 2y plus 2z. So this gives you the equation of a plane by using this normal form. So the important thing is to figure out the vector that is normal to the plane and know that the position vector of any vector on the plane, when dotted with the normal, the unit normal, will give you the distance from the origin to the plane, and the distance is known to be 5. So it doesn't matter where if you look at the diagram we drew up here, it doesn't matter where you put the vector. Even if it is here, the projection will still land on, it will be the same distance, this same distance p. If you project any vector on the plane to this unit normal, since the perpendicular will start from the terminal point of that point to the terminal point of the normal vector, the distance doesn't change regardless of which point on the plane that you pick. And therefore, this is true for any point on the plane, and you can use it as an equation of a plane. That's what we have done in the example, and we have the answer, the question as x plus 2y plus 2z is equal to 15. So that's the normal form for the equation. So that's what we call the normal form of the equation of a plane. So I hope you have gotten that. There's another form in which we can represent the plane. So here we use the fact that if you have any 3 points on the plane, these points will uniquely determine a plane. So if you have any 3 non-collinear points, they are not on the same line, then they all lie on the same plane. There's only one plane that contains those 3 points. So that's why we say it uniquely determines, the 3 will uniquely determine a plane. So using that property, we can denote the position vectors of the 3 points as A, B, and C. Now, if R is any other point on the plane, then these 3 vectors, R minus A, B minus A, and C minus A, will be on the plane. So we saw earlier that if you have 3 vectors on a plane, volume of the parallel pipe formed by the 3 vectors is 0, right? So if you know that these 3 vectors are on the plane, then the volume of the parallel pipe formed by these 3 vectors will be R minus A dot B minus A cross C minus A. And this should be equal to 0 because they're all on the same plane. So here what happens is, what you don't know is R, the position vector. But now these are all known. A, B, and C are known. So you can work this out and get the equation of a plane using this. So I think there's an example for this. So here is the diagram that explains all this. So we take A to be this point, x1, y1, z1. The position vector for B would be x2, y2, and z2. And the position vector for C will be x3, y3, and z3. And then x, y, z is any other point on the plane. So you can see if this is a point on the plane, then this vector from A to this point will be on the plane. The other vector from C to A will be on the plane. And the other vector also from A to B will be on the plane. So these three vectors are on the plane, and therefore they are the triple product for the three vectors should be equal to 0. So we find the position vectors for this R minus A and B minus A and C minus A as well. So once we find all these components, we can form the matrix R minus A dot in brackets B minus A cross C minus A will be equal to the determinant of this matrix. We saw this earlier. That it means these are the components of this vector. This second row are the components of B minus A, and this third row are the components of C minus A. And we obtained this earlier. We already know them because we had A, B, and A. We also had R, so it was possible to get the components of R minus A like that, the components of B minus A, and the components of C minus A. So once you have those, you simply put them in the matrix and equate to 0. So this will give you the determinant. Once you work this out, you will get the equation of the plane. So that's another form of the equation of the plane. Once you know 3 points on the plane, you can use this to determine the equation of a plane. So the previous normal form required you to have a vector that is normal to the plane and also to know the distance from the origin to the plane. If that is known, then you can find the equation of the plane. This second method for the 3 points requires you to know 3 points on the plane. And once you know the 3 points, you can determine the equation of a plane using this matrix. So now it can be shown that this determinant is the same as this determinant of this 3 by 3 matrix is actually the same as the determinant of this 4 by 4 matrix. I will not go into the details of that now. That can be a challenge for you. Try to show this, that this determinant of this 3 by 3 matrix is the same as the determinant of this 4 by 4 matrix. So this one simply means you list the components of any point on the plane first as x, y, z. Then the components of the second point, of the first point that is known, components of the second point that is known, and components of the third point that is known. And then add a column on the right that is all ones. So you just add this column here that is all ones. This one may be easier to recall than this one, but they both give you the same determinant, 0. I think I'll leave that as an exercise for you to check that these two are indeed representing the same thing. So the next example says find the equation of a plane that passes through these 3 points, 1, 1, minus 1, 1, 0, 2, negative 1, 1, and 1, 2, negative 1. So using the formula from the previous part, and if we pick any point on the plane, we name it x, y, z, and that's the position vector. Then we can obtain R minus A, B minus A, and C minus A. So B minus A is simplifies to 1, negative 2, 1. C minus A simplifies to 0, 1, and 1. and we can obtain the equation of a plane by simply working out this determinant. And it works out to, when you compute this determinant, you end up with x plus y plus z minus 2 is equal to 0. I left out something. Okay? No, I didn't. There's minus 1 here and minus 1. That gives you minus 2. That is what moves to the right-hand side. So your final answer will be x plus y plus z is equal to 2. That's the equation of the plane. So any point on the plane will satisfy this equation. So there's another way to look at it, what we call the algebraic form. So in general, an equation of a plane in 3 dimensions will take the form ax plus by plus cz plus d is equal to 0, where a, b, c, and d are all constants. So if you find any equation of this form, it will be a plane. So we need to indeed prove that this is a plane. To be able to do that, we need to pick any 2 points in the plane and show that any point on the line joining the 2 points is also in the plane. Tuko pamoja? Hello, you can hear me?
Yes.
So I didn't hear anybody saying amen, Bwana. This was a big point I have just put across. Eh? So I'll repeat again. So we want to confirm that this is indeed the equation of a plane, but we want to use some algebraic techniques. We avoid the vectors for now. So for us to do that, the strategy would be the following. Pick any 2 points on the plane and show that any point on the line joining the 2 points should also still be in the plane. So you pick 2 points that satisfy this equation and show that any point on the line joining the 2 points will also satisfy this equation. That guarantees that the 2 points are on the same plane. That makes sense, right?
Yes.
Yes. So that's the strategy. So let's go into the proof with that strategy. So let's take the 2 points to be P and Q, and the coordinates would be x1, y1, z1 for P, and x2, y2, z2 for P. So we need to find a point, some way of expressing any point that lies on the line joining P and Q. So that can be done in the following way. Pick a positive number lambda, then lambda x1 plus x2 over lambda plus 1, and lambda y1 plus y2 over lambda plus 1, lambda z1 plus z2 over lambda plus 1 will be a point on the line. So how do we know this is a point on the line? So we assume the ratio can be written in the form lambda to 1, right? The ratio of the point from the point, if the point is between P and Q, it will be some distance from P, and it will also be some distance from Q. Now the ratio of those 2 distances can be assumed to be lambda to 1. You can ensure it is in that form, right? So then you can write the coordinates of that point in this form, as long as the ratio is in the form lambda to 1. You must have done this in SMA 105.
Yeah, we did.
Yeah. So this if any point, so you can keep changing lambda to find new points, but any point on the line between P and Q will take this form. So our work is to put this point in the equation, in this equation up here, and confirm that indeed this point satisfies this equation. So if you plug this back into the equation, we will end up with this, right? That's the x coordinate, that's the y coordinate, that's the z coordinate. We end up with this. So after doing a bit of work and simplifying, we end up with this form that the first term here is ax1 plus by1 plus cz1 plus d. And the second term is ax2 plus by2 plus cz2 plus d. But now we remember, we said that these 2 points, P and Q, are on the plane, right? If they're on the plane, they must satisfy this equation. So if I have ax1 plus by1 plus cz1 plus d, I will get 0, right? The same for x2, y2, and z2. I will not get 0. I will get 0. So it means this quantity here will be 0, and also this quantity here will be 0. So I have shown that this point, point here, with this as a coordinates, when I put it back into the equation for the plane, I obtain 0. So these points actually satisfy the equation of a plane and must therefore be on the plane. So what we have done is picked any 2 points on the plane and shown that any point on the line joining the 2 points must also be on the plane. And therefore this must be the equation of a plane, right? So algebraically, again, we show that the equation of a plane will always take this form: ax plus by plus cz plus d is equal to 0, where a, b, and c, and d as well are constant. So anytime you encounter a plane in this form, an equation in this form, it's the equation of a plane. So a few remarks we can make. If you have an equation of, if d is 0, rather, in our previous setup, so that ax plus by plus cz is equal to 0, that will be a plane that goes through the origin. The point 0, 0, 0 is on the plane. Because if you put 0 here, and 0 here, and 0 here, you get 0. So the origin is also on the plane. So the plane must go through the origin. Then the next one is for the plane ax plus by plus cz is equal to d. This vector a, b, and c is normal. Is a normal vector. If you go back to the normal form of the equation, you will see why this is true. These coefficients a, b, and c of z form the normal, will give you a vector that is normal to the plane. So that gives you a hint again. If you're looking for the normal to the plane, you just need this vector whose x component is a, y component is b, and the z component is c. That will automatically give you a vector that is normal to the plane, as long as you have the equation of a plane. So now the third form of the plane that we can come up with is what we call the intercept form. So this one requires us to pick the points at which the plane cuts the x, the y, and the z axis. So if those points are listed as follows, the first point at which the plane cuts the x axis would be a0, 0. The second point is 0, b0, and the third point is 0, 0, c. So if it's a plane through the origin, all these points will be 0, 0, 0. But if it's not through the origin, then a will have some value different from 0, b will have some value different from 0, and the same for c. So if these are 3 points on the plane, remember we have the 3-point form of the plane. You can just apply that 3-point form to these 3 points. But now these will be the points at which the plane cuts the x, y, and z axis. And that will be the determinant of this matrix. If you find the determinant of this matrix, it will be this: bcx plus cay plus abz minus abc is equal to 0. We can divide throughout by ABC. We can move ABC to the right-hand side so that we get this equation. If you divide throughout by ABC, then we will have x over A plus y over B plus z over C is equal to 1. Can you confirm that these two equations are equivalent? So it's important for you to come with a pen and a book to this class, because you cannot, I keep telling you, you cannot learn mathematics by staring. So are you staring or writing?
You have already written it.
You have, hey, you guys are chap. But have you confirmed that it's the same? Because
Yeah.
you really have to do these calculations yourself. That's the only way you can be sure about your knowledge of the formulas that appear here. If you don't do it by hand yourself, when you meet them in the exam, they will look strange. So if we know the x coordinate for the point at which the plane cuts the x-axis, the y coordinates, point at which it cuts the y-axis, and the z coordinate for the point at which it cuts the z-axis, then it's easy to simply write the equation of a plane in this form: x over A plus y over B plus z over C is equal to 1. So you could also think of this as follows. If you go to the algebraic form of the equation, if you have it in this form, ax plus by plus cz is equal to d, if you divide both sides by d, you will have 1 on this end, and here you'll have a over d plus b over d plus c over d. Then with that, you can easily obtain the x coordinate for the point at which the plane cuts the x-axis. So you want this to be x over some number. So a over d multiplied by x is the same as what? X over d over a. Is that correct? If you divide x divided by d over a is the same as x, is the same as ad multiplied by x. Is that correct?
Yes, that's correct.
Yeah, so you can find the what would appear at the bottom like that and end up with a new, then you can quickly find the points at which it cuts the x-axis, the y-axis, and the z-axis. So you can connect the two and use it wisely when solving problems. So I'll give you a job to do. Find the equation of the plane that makes equal intercepts on the axis passing through, and it passes through the point 1, 2, and 3. So when we say it makes the equal intercepts on the axis, it means if the intercept on the x-axis is A, the intercept on the y-axis will also be A, and the one on the z-axis will also be equal to A. So the points you are looking for here will be A0, 0, 0A0 on the y-axis, and 0, 0A on the z-axis. Those are the intercepts. So you can use the intercept form to solve this problem. The first person to solve this one will get 50 MB. Twende kazi bwana. You have 3 minutes. So you have to solve this within 3 minutes. If you go beyond 3 minutes, you don't qualify for the 50 MB.
Six.
So you put the answer in the chat. I'm going to check in the chat. The first person to put the answer in the chat will get the 50 MB. We don't want a number. We want an equation. Read the question. The question says, find the equation. Find the equation of a plane making equal intercepts on the x-axis. So that is one condition you're given. And then the second condition is that the plane passes through the point 1, 2, 3. So what I want is an equation of a plane. You can use a 3-point form to solve this. So in the chart, I do not want a number. I want an equation. So Ngare has found x plus y plus z is equal to 6. So let's see if we agree with the Anthony's number agrees with Ngare. Omolo has a different answer. So Omolo, no means what? You have abandoned your answer, or you are sticking with your answer? Oh, that's a major mistype, man. So what's the correct answer, Omolo? Joel, what we need is an equation, not a number. So let's see what we get. Here is the solution. So we know that the intercepts are the same. If we use the intercept form of a equation of a plane, we'll have x over a plus y over a plus z over a is equal to 1. If you multiply both sides, you have x plus y plus z is equal to a. But we know that the point 1, 2, 3 lies on the plane, right? So since it lies on the plane, it must satisfy this equation. So we can just substitute 1 plus 2 plus 3 should be equal to a. And that means a is equal to 6. So the equation we are looking for is x plus y plus z is equal to 6. So let's see, the winner was who? Gary is the winner.
Yeah.
Gary is the champion now. So Ngare, I think you will get 50 MB, and on top of that, we are going to award you the championship status.
Yeah, thanks in advance.
So you are officially the owner of the bragging rights. Eh?
Yeah.
But you better be careful. Someone might take them away from you. You have the title of a bragging rights for mathematics. You can walk around and say you're a mathematician.
I will prevent it from Omolo.
Huh?
I will prevent it from Omolo.
You will defend the title. So you may be required to defend the title in the next class. You might lose the belt if you're not careful.
I'm the default owner of that title.
You are the default owner. But now you did not give the title, the answer in good time. Eh? So you have to be fast also. So that is all for this class. I shared the notes with John. I think he posted them on the. Hopefully, he posted them on the WhatsApp group, and all of you have them. I'm also going to put the link to the notes on the SOMAS platform. I will try to do that today. I need to do that for all the units I am doing. Then once I put the link, you'll be able to download it anytime. I will also set up the video and put the links again on the links to all the videos on the SOMAS platform. And also, once I put this video up, I will share it with John. So remember, we made some correction when I was presenting. I think it was at this point. You need to keep that correction in mind when you're reading the notes. Where was the correction? I think it was here. When we were working out the normal form of the... So in the description here, it says that n is a unit vector from the origin to the plane. But a unit vector may not even reach the plane, or it may go beyond the plane, depending on the normal to the plane. So I made that correction when explaining this. Make sure you go to that part of the video and get this explanation correct, because what is appearing in the notes may not be is not the correct explanation, because it says the unit n is a unit vector from the origin to the plane. But that is not correct. It's just a unit vector in the direction of a vector that is normal to the plane. So you have a vector that is normal from the origin to the plane, and n is just the unit vector in that direction. So n is not the whole vector. It can only be the whole vector if that distance from the origin to the plane is 1. If not, then it won't be. It will just be a portion of the vector. But it is in the same direction as a vector that is normal to the plane. So please note this correction so that you don't read the notes exactly as they appear. I have made the correction in the video. So when you read the notes, you need to make that same correction. Hey. Hey. Aguer. Iwinjo.
Nivo.
Emwanyita. Gare. Wanyita. Good. Okay. Kuna maswali? So otherwise, if there are no questions, I can wish you a great day, but we will be meeting again in the evening at 4 o'clock.
Yeah.
For SMA 108. Okay, looks like there are no more questions, so we shall end the class. And